each team that proposed the problem that we used yesterday explains briefly their idea of the problem and how to solve it. So who was that person? I know it's Pablo. Someone.
These are known as the count words. That's for the characters from the story. And the characters know these words and they want to count in how many ways they can form another word, another given word, by concatenating words from this set. So for example, they want to form the word programs. They can do it by concatenating these two words that they know. So, given a dictionary, the question is how many ways you can do this in obtaining a given word. And it will seem to be a straightforward dynamic progression problem. There was some people having problems with the memory data thing, but not sure how the online judge figured that. But anyway, when you want to form a word, the choice you have to make is which word will you use as a prefix of this word. So, for example, here you only have one choice. The only word you know that's a prefix of the word you want to form is pro. So you have to use pro. And in how many ways can you use pro as a prefix? Well, in the same number of ways you can form the rest of the word by concatenating words from the dictionary. So this reduces to a smaller instance of the same problem. So the sub-problem here is for a given suffix, in how many ways can you form that suffix using words from the dictionary? So you have basically n states, one for each suffix. And in each suffix you have to choose one word from for each suffix you have to iterate through all its prefixes, and for all prefixes that are contained in the dictionary, you count that prefix plus, you count the number of ways of forming the rest of the word, and the result. And the base case is that you can always form the empty word in one way, which is using no words from the dictionary. So that's basically the requirement. And there are more than one way of implementing it. One way is very efficient using the tree, a prefix tree, try, in which you can, for each character you add to the prefix you're considering, you just jump to the child node in the tree. So complexity for this solution would be, well, let's call the number of words here T, and L the length of the maximum length of the word in the dictionary. So it should be for each prefix, for each suffix. So L times for each prefix. You don't add the complexity by just jumping to the next character in the tree, because that will be over one considering the implementation. So it will be just L times L squared. However, intention was that an easier solution would also be correct. So you could also just form the word and look it up in the dictionary using a set, for example. So if you used L times L squared times log D, which is for each suffix, you look up its prefix in the dictionary using time L log D. Well, this is L cubed because you have n state. This should be enough. Yes, even this solution, some implementation will work in accepted.
So why is a cube and then a square?
Because you have L states for each state.
Right. And n prefixes, right?
Yeah. Oh, yeah.
So that's it.
L squared. But this one is still like L cubed because each computer is in the table.
Right, yeah, he's good. That's fine.
So this should.
Are there any questions? Did everyone understood the explanation? Yes? Okay, perfect. Thank you for your. Okay, so anyone here to come next?
My problem is Master Yoda's problem, and you need to calculate the size of the largest common palindrome of a set of words. And when you have a palindrome, and this palindrome is inside all the words, you can take off the first and the last characters, and this palindrome is also contained in all words. So you can do a binary search and check if for all sizes, if there is an answer with that size. And you have to check to odd sizes and for even sizes separately. So you are asking if for a size T there is a palindrome with that size that this palindrome is inside all words. So you can, for every word, you can use hash, a polynomial hash, to compute all the hash for all substrings of size T. When you have this hash, I don't know, you can call it hash 1. You can reverse the string and apply the same function and build a hash 2. With these two hashes, you can check if a substring of size T is a palindrome in constant time, because the positions are I and j, and the hash 1 in the position I should be equal to hash 2 in the position j. If that happens, then T is a palindrome. Now you can check in constant time, and you can, for all words, put all palindromes, all hashes for the palindromes on a vector. So you stay with 10 words, n words, you should stay with n vectors. And now you must check if there is a palindrome that's contained on all these vectors. To do this, you can sort them, and for every hash here, you can binary search on the other vectors. If you find at least one, the answer is yes, and if you don't, the answer is no. Okay? So the overall complexity is log n to the binary search times n to compute the hashes.
Sorry, you're using n as the length or the number of words?
The length you are searching. You can search from 0 to the length of the
No,
word.
because here n is the number of words, not the length of the words.
So log n times n for each word and log n. The slowest stages is the sorting and searching phase. So O and log squared. Question?
Just one quick comment. So everyone knows why I can, or he or whoever, can calculate all these hashes in linear time. Even though each hash depends on t values, not just one value. But I mean, the sliding window, for polynomial hashing, the sliding window is easy to calculate because it's just looking at the piece of the string as a base the modulus you are using for a hash number. So adding characters at either end or moving the window and everything is all just arithmetic operations in base B for something. Okay? So we can, from this hash we can move to the hash that is one character to the right with just constant time operations. Okay? Otherwise, calculating all these hashes will take time. The length is m times t, right? Have m substrings each with size t. Okay. Okay, so I just want to make some comment about an alternative solution for this. So it's not that different, but so for finding palindromes string, well, there's an algorithm of finding palindromes that has a known algorithm that finds all palindromes in a string, and then with hash or whatever you can do more or less the same trick. Put all palindromes in a set and then find which one is doing everything. And since the algorithm to find all palindromes is, if you want only maximal palindromes, is more or less linear, then the overall complexity thing is you can remove one node from the other. But that's really just a particular algorithm for palindromes. So another good way of looking for palindromes is this trick of reverse the word and find the shared substrings. Right? Because palindrome is just the substring that is shared between the word and the reverse of the word. More or less, the same position. So you can do that by building the suffix array of the concatenation of both the word and the reverse word. Right? If we build that, we can check with the suffix array and the longest common prefix array. We can check at every position. We can find maximal substrings that are repeated that are shared between the word and the reverse of the word. And then we can, since we know which position each substring is positioned in the suffix array, we can check whether they are in the correct place, and we can check whether there's a palindrome or not. Okay. In this particular case, if we put all the words into a suffix array and all the reverse of the words to a suffix array, we can more or less do the same trick, but to find shared palindromes among all the words. Right? I mean, to search for a substring that is shared among all the words in the suffix array is just what we did yesterday with the file retrieval problem. It's more or less that trick. It's just finding a consecutive part of the suffix array that has at least one suffix in each of the words. Right? And then with the same suffix array, we can check whether that contains a palindrome or not. Okay, I'm sparing the details because there's a lot of fraud. If you want to practice suffix array, just think about how to solve it. Okay. So anyone else? Who wants to come? Any other comments about this problem? Any other solution? No? Okay. So who wants to come next? There's plenty of problems left. Good.
My problem is the G. So first I will start with a simple problem, and then I will get to the main problem. That's all. Well, suppose that you have a problem that gives you a grid, right? Coordinates. X and Y, right? And give you values in each position. In each cell it gives you some value, right? And then he asks you given some position X, Y, and an integer B, calculate for me the sum of all positions that are at most 3 positions away in Manhattan distance from this position X, Y, right? Well, to solve this problem, you need to first observe that whenever you have a point, all the points that are 2 positions away in Manhattan distance from it, from like some sort of triangle, right? Okay, so looking this way, like turning your hand like 45 degrees to the right or to the left, you can see that you can rotate all the coordinates, right? So when you rotate all the coordinates, you have a grid that will be like this. But all the coordinates will be sort of like this. Okay, so if I get some square here, yeah, that's it. So if I get this square here, after rotate the grid for 5 degrees, I will see if all positions in this square will be like this. So here it is 1. So all positions here, the original grid will be 1 position away, Manhattan distance, from that point, right? Okay, so to rotate the grid, it's easy. One can prove that if you do it this way, you can rotate the grid for 5 degrees to the whatever. Okay, so now you have the grid rotated, and now you need to build a data structure, to use a data structure that will give you the GCD of some rectangle, right? Well, you can use PIG, two-dimension PIG, because the GCD has also a recursive function. Okay. But you can use segment tree, a two-dimensional segment tree, right? Okay, so now you know how to rotate the grid, right? And all you need to do now is use a two-dimensional segment tree to calculate the GCD of some rectangle and to change some cell of the grid, right? Okay, so let's solve the problem, right? Well, I had some problem during the contest. That's why I get like 6 that 6 were answered my own problem. But the problem was the memory limit on memory. But well, what I did to solve was, well, in every segment 3 you do like this, right? Prototype this one. And I changed it to 3 times and get that set.
Do you ever understand the overview of the solution? So I would like to comment a little bit about this two-dimensional segment tree, how to implement, and also one more comment. So the two-dimensional segment tree is, so the two-dimensional plane or the two-dimensional grid in this case is just the cross product of two one-dimensional intervals, right? So a matrix of n by m is just taking two intervals. By cross product, I mean the actual the cross product you learn about in primary school, right? When you take all the pairs of all the pairs that has one element from this set and one element from this, right? This is a matrix of n by m. Okay. So basically, what we need to do is cross product two segmentaries, right? So each node. So in regular segmentaries, we have nodes representing intervals properly aligned here. So in two-dimensional segmentaries, we will have nodes representing submatrices or contiguous submatrices of the matrix. Okay? So we will have the root node that will represent the whole matrix, and then we're going to split it into 4 pieces, and then each of these split into 4, and so on and so forth. Okay? And again, if you do the implementation top-down, it's just a matter of changing a little bit the splitting code for the perfect boundary conditions, and it's going to work. But also, so that's if you never implemented the two-dimensional segment tree, it's a good idea to go ahead and adapt your own code for the regular segment tree for this, because doing it for the first time, you run into a couple of problems, like with the edge case and how to do exactly the splitting math and everything. And it's not good to start doing that in the middle of a complex study. Also, okay, so this trick about rotating the coordinates is good because afterwards you have rectangles, and rectangles are easy to deal with. But at least easier than this rhombus you have. Okay. But you can also do the problem directly on rhombus because, well, you can, because if you can do it rotated, you can also do it directly. But because you can think, so by triangle inequality, if something is at distance d from a given point, okay, and we take points at distance d over 2, then anything that is at distance d over 2 of them is also at distance d or less from here. Okay, so we take any point, and we know that this distance is d over 2, and then any other point at distance d over 2 from here is going to be no farther than d from here. Okay, this is just triangular inequality. Okay, and also, just by looking a little bit at the drawing, if we take the center point, and we get the d over 2, and we subtract and add d over 2 to each coordinate, we can see that all points that are at distance d from this are at distance d over 2 to at least one of these. There's some overlapping, there may be some overlapping. Okay? If d is odd, then we have to do something with the border, but it's just a matter, I mean, we can just go d over 2 here, and then check this and this and this and this. Okay? And the same for all directions. So more or less we can build the two-dimensional segment tree thinking of this kind of region, because this is the same invariant you get for rectangles. Rectangles is more obvious. Yeah? Okay, if I have a rectangle here, I can split it into 4 sections and analyze each section separately, and they are disjoint and everything. But this kind of area, this kind of rhombus area, can also be split into 4 areas that look more or less the same. Okay? And since we are using an operation like GCD, if there's overlapping between the areas, it doesn't really matter, because the GCD between two, I mean, adding repetitions of the same values to big GCD is not going to change the result. Okay? So we can just say, okay, for each distance that is the power of 2, I'm going to calculate the result for the area centered in each of the squares. Okay, so the result. Sorry. So the result for distance d in one square is just the result. So for distance 1, the result is just the value in the squares, and the result for distance d is just the result for distance d over 2 in this. The GCD of the result of distance d over 2 in this form, like neighboring, let's say, squares. Okay. So based on these observations, we can build the segment tree doing this. So this and the levels of the segment tree represent the distance we are trying to analyze. Okay, and then everything works more or less like the segment tree. When we update, we have to update all the variants of the square we are updating. Okay, but this really is exactly the same as this, only you don't go through the observation of how to rotate. You don't rotate explicitly the coordinates. Okay. I guess it's probably basically taking this. Basically, if you take this code and compose each time you do math with the coordinates, you compose with this transformation, you probably get something like the code for this solution. Because it's essentially the same thing. It's just doing the coordinate the transform of the coordinates in a different moment or a different way. Okay, this is just a comment of how to. Because I think this observation may be nice to analyze other problems as well. That these kind of areas, it's nice to think when you have these kind of areas, to think how they can be split to like sub-instances like of the same, because well this this enables you to use some kind of dynamic programming solution or this kind of thing. Okay, any questions or more comments? Different solutions for this? Okay. Who's next? Or who wants to be next? I don't want to be calling out like, okay, now the author of this problem. You are going to be explaining eventually. So. No one is going to volunteer? I don't want to explain your case.
You're calling to explain any problem?
Sorry?
You're calling anyone to?
Yes, that's someone that still has his problem not explained, that comes forward and explains the problem.
I can a bit like the side scene to someone explain.
Sorry?
The side scene to.
Yeah, come here.
So, the problem of the sightseeing tour, you had some tourist place that you want to see, and you can see them from the top of the mountain. And on this mountain, you have several binoculars. Every binocular has some dots like 1, 3, 5. And each binocular covers some bridge points. And the tourists came to the owner of the binoculars, and they want to see all the tourist places. So they want to choose some subset of the binoculars in a way that they can see all tourist places. There's several set of binoculars that makes the tourist able to see every tourist place. So the difference is that every tourist is willing to pay a different amount of points to see the tourist place. So let's suppose you can see that there's a solution 6 that takes this binocular and this one, and let's say there's another binocular. There's also a solution with 5 that takes this binocular, covers up to here, this one covers up to here, and this one. And the solution is also 6, so it's 5, okay? So you have 2 different solutions. One takes 6 points, and the other takes 5. So let's say a guy comes with 5 points, 6 points to you. So one way that you can do for him to pay more is like you can take out this binocular and this one here. So here the only choice he has is take this one, and this one. So you end up paying 9 points, even though there's a way to pay less than 9 points. So every tourist has a different combination of binoculars you have to take to make it pay more. So what you have to find is if the tourist is willing to pay X points, and you have combinations of, you can find a combination that takes A1 points, A2, A3, A4. The biggest value you can charge this guy is the biggest value that you can find of points. Let's suppose you can find points like 1, 3, 6, 9, 11, 12. So then you can force some set of points that makes the guy pay these values. And the guy is willing to pay like 10. So you do a binary search here and you can find the value, the maximum value that he is willing to pay. It's nice. But the problem is you have 10 to the power of 9 guys that's going to see the tourist place. And let me explain how the carriage works. The carriage works. So a carry is you have 10 to the 4 carries, and a carry say 2 numbers X and Y. And that means that the first guy is willing to pay X points, the second guy is willing to pay X plus 1 point, the third guy is willing to pay X plus 2, so on, until the last guy that is willing to pay Y. But if you were to process for every guy, we'd have to process 10 to the power of 9 guys. But there's something you have to see about the problem is that you have at most 30 binoculars, and the price of every binocular is up to 5 or 10, I guess. The price of every binocular is up to 10. So if the solution is to use all binoculars, you use no more than 300 points. So you don't have to process for every guy. You have to just process for the guys that are up to 300. So how was the solution? First thing, you find all possible values that you can use to make the guys pay the subsets that charge all the possible values. You can do this by dynamic programming, and I'll explain. Everyone solve using dynamic programming? 14 solve.
Yeah.
Because so what you have to do is you have the places here. And you keep track. I explain a bug solution and then I say why it's wrong and explain the correct one. So since the points are in order, one thing that you have to do is you can sort the binoculars by their start. Okay. So after you sort by their start, you have some binoculars that start at this point. So for every binocular, you can choose if you want to use it or not. And suppose you use it. Now you keep track that the last binocular used was this one, and when you try a new binocular, suppose the next binocular is this one. This one will be useless because the last binocular already covers everything this one covers. Suppose the next binocular is like this one. Then you can choose to use this one and start here next time, or you can still keep trying to use every binocular on the way. So you can do like a DP, the binocular, current binocular, and the last binocular used. And the price you already. So even though I call this DP, it's just a DFS, so you can do a DFS in this kind of graph to find all possible prices you can get today. So all the prices are the values that you can use to choose subsets. So you can keep going here to reach the end, and the price to reach the end is the price that you are able to charge that price to the guys. But this solution is flawed because of this case here. So if you keep the last one, let's say you start with this one, then you choose and you cover these two binoculars. And then now you choose this one. This one covers two binoculars, yeah, it covers this one. So you can go and choose this one too. Now you can choose this one to cover this last binocular here, and you're done. The problem with this is that this binocular is the guys it's covered is this one and this one are also covered by this one and this one. So this creates a problem with this solution because we also need to keep track of the last guy, the guy before the last one. So you can, when you try to place this one, you see that this guy here also covers this guy, and when you put this binocular won't cover anything. So the way to fix the solution is also put so now you just run SDP here and find out the possible prices you can get. And for the carriers you can do accumulated array, like I don't know English word. You just for every price up to 300, you just store the biggest price you can charge for this one. And for every price after 300, the biggest price you can charge is the price for 300. So you just answer the carriers up to 300 for everyone. And then for the remaining, you just multiply the number of guys after 300 by the number you can get from it. Any questions?
No. Let me just do a quick recap of this last part, which is the kind of complicated observation. It's a nice observation. No, the dynamic programming thing. So the idea is that you add the binoculars on a left to right kind of way, right? In order. So what can happen, like he showed in this example, is that when you add one, you make some previously added, because you in the dynamic programming, the idea is that you forget information, right? Everything works because you don't need to keep all the information, all the history, which subset of binoculars I'm choosing, because otherwise it will be just be brute force. At this point, I decide, or he decides, that he only cares about, okay, I covered up to this part, and I'm already charging this amount, and so on and so forth. Okay? So the idea is to forget some part of the history to make a lot of sub-problems be into the same equivalence class or something like this. Okay? So what he was saying is that since I don't know which are the actual binoculars being used, when I add some binocular, it's possible that I made one binocular obsolete. Right? Obsolete, by obsolete I mean I'm between the newly added binoculars and some previous binoculars that I forgot about. I covered all the sightseeing places the last binocular was seen. And it's important to know that this can only happen with the last binocular, right? I mean, if I manage to make the last one not obsolete, I will also not make obsolete the previous, because since I'm adding the binoculars in order, if I make something obsolete at one point, if it's not the last one, then it was obsolete before. Okay? Because I didn't cover any, whatever I covered that was already covered by the last one. Okay? Is this clear? So if I manage to avoid making the last one obsolete, I'm also not making any other of the binoculars that were added obsolete. Okay? It is possible that we may make several binoculars obsolete by adding one, but if that happens, it's going to include the last one of the next last one. Okay? So by adding this last binocular, he remembers, okay, I had to cover up to here, and then currently I cover up to here. So I know that I cannot cover this whole region with the next binocular, because that will make this one obsolete. Okay, so I know that I need to cover more than I had. I can overlap a little bit, but I cannot overlap all this region. I have to leave at least the one that comes here. I have to leave uncovered. Okay? This is a nice trick or a nice property of this kind of intervals. It is a condition of maximality of intervals that can be used in several ways. Okay. Right. Okay, let's do one more and then take a small break. Better to be the last one now than the first one after the break.
My problem was the order crossing. So I'm going to briefly explain the flow statement. You have a very long corridor and some words on it. Each word has an energy pi. And a word with energy pi is able to create a square of length 2 times pi squared of deadly lasers, which you can pass through. Every word creates such squares. Square centered has a word, and you can change the energy of some words in order to make crossing possible. Okay, and you need to find what is the minimum absolute difference between a starting position and an ending position, such that the end position is crossable. Is it clear? Okay. First thing you have to notice is the condition for whether a configuration allows the curve to be crossed or not. And it turns out that the crossing is possible if and only if there is, the corridor is not crossed. The crossing is not possible if and only if there is a sequence of overlapping squares that connects the left wall to the right wall. This clearly blocks the path, and it's not hard to see that if such a thing does not exist, then crossing is possible. So we don't want this thing to happen. The second thing is that we only want to minimize the absolute difference between the ending configuration and starting one. We don't need to minimize the number of changes or something like that. So the ending configuration can actually be very different from the beginning one, as long as its energy is as close as possible to the starting one. So in order to find the ending configuration, we can just try to find what is the maximum possible energy a configuration can have, such that the crossing is possible. Because let's call EF such energy, the maximum energy such that exists a configuration that allows the curve to cross, and E as the starting energy. If EF is strictly lower than ES, then the answer to the problem is just ES minus EF, right? Because we can't do better than this. Okay. And if EF is greater than or equal to ES, then the answer to this problem is 0, because you can just pick any configuration with EF energy that is crossable and choose any set of words that reduce their energy until the energy gets equal. Because reducing an energy of words is never too bad, right? If a configuration allows the curve to be crossed, then if I choose a word and reduce its energy, the curve would still be crossable. So
wait. So maybe you should explain exactly what are you calling EF, because you can have like an isolated square that is initially small, and you could make it bigger.
yes,
But is that allowed by the thing?
yes.
Okay.
You can change to any value you want. You can also increase the value of energy of the word. Okay, so our goal is to find EF. Okay. And so to do this, we just assume every word starts with maximum energy, which is 200 by sigma, and try to reduce the energy as little as possible. Okay. The same thing is maximizing the energy. So we have very large squares, and we want to reduce them as little as possible to make the crossing possible. Okay. And playing with words with variable energy is bad. So instead of thinking this way, you can see the problem as if a word has energy pi, instead of it creating a single square of length 2 times pi squared, it creates 1 squared for every unit of energy you have. So this would be 2 times 1, this is 2 times 2 squared, 2 times 3 squared, and so on. Okay. And now the problem would be eliminated as little as possible squares. Okay. It's not hard to see that the problem remains the same. Okay. So now we're not reducing squares, we're just eliminating some squares. Okay. Good. Okay, now our problem is we have lots of squares. And we want to choose the least amount of squares possible to make the corridor crossable. And this looks like a minimum code problem, right? Just what we actually are looking for here is to choose the least amount of squares to disconnect the left wall to the right wall, right? So we can just build a graph. This would be the left wall to the right wall. and each square would be a vertex 2. And we connect a square with the left wall if they intersect. We connect the square with the right wall if they intersect. And of course, we connect two squares if they are relative. The graph would be something like this. And now the problem is to find the minimum cut of this graph, but not the usual minimum cut, the vertex minimum cut. Okay. And in order to solve this problem, in order to reduce this to the original minimum cut problem, you can just duplicate each square. If the square overlaps with the left wall, you create an oriented edge on the left wall to, let's call this vertex 1, vertex 2. So each square will have two vertices. You create an edge from the left wall to the first vertex of the square. If it overlaps with the right wall, you create an oriented edge this way. Between the same square, you create an edge this way. Well, capacity, forget capacities. These edges have infinite capacities. No, well, this edge will have infinite capacity. This will have a negative capacity. If two squares overlap, you create two edges. What's that? Now the problem is reduced to the usual minimum cut problem. That's pretty much it. No question.
So notice that, so two things. One is that the upper bound given for the energy was unnecessarily big. I mean, not unnecessarily big. You can ignore the energies that are greater than 33 because, right? If the energy squared is greater than the length of the corridor, then just that square is going to cover the entire corridor, right? So nothing can have an energy such that the square center at that point covers the entire corridor. That reduces the number of, reduces the maximum energy a given point can have in a solution. Okay, that means, so in this view he explained, you have the corridor, you have the point, you have all these squares around the point. So up to some energy, the squares alone start intersecting with both walls. Okay, so this we can remove directly without even putting them into the graph, and this greatly reduces the number of vertices and edges we need to process when we do minimum cut, which is the more expensive part of the algorithm. Okay? That's one thing. The other thing is that, okay, you said that the idea was that if you had someone with energy 1, it was allowed to change to energy 2. Right? So you could increase the energy of someone. So when you get to make these squares, you have to make them up to the maximum energy for everybody. Right? But even if this weren't allowed, if the magic would only reduce the energy of some of these guards but not increase the energy, then it really doesn't matter. It's just a question of, because this is how I originally thought this statement was meant. So it's the same. We just, if some guard has energy 3, we just build the squares 1, 2, and 3 for that guard and not the bigger ones. Right? Because this thing is how many I have to remove. So the only change if the maximum is set or it's possible to increase is whether I start with more squares or not. Okay? So this problem is really kind of IOI kind of problem, where the actual meaning of the things is hidden behind the story or the, because this really doesn't look like minimum cut. you really have to see that. So it's besides the actual algorithmic part, it has a nice thing to practice to keep drawing and keep thinking about the problem until something appears that is not immediate. Sometimes you read the problem and you say, okay, this is obviously dynamic programming. It may be extremely difficult, and you may never find which is the appropriate recursive function, but you very immediately see that it's dynamic programming, or it is some kind of flow, maximum flow or something, even if you don't end up solving. In this case, it's the opposite. Once you get to the part that you see it's minimum cut, the rest is easy. The hard part in this program is getting from the statement to something that looks like minimum cut. Okay, the rest is just working on details, but it's more or less straightforward. So it's good that you can practice also this part, or this kind of problem. Okay, so let's just, since we get to the half of the problems, let's just take about 10 minutes break and come back.
Começou a desenhar aquele vídeo lá, você começou a desenhar o vídeo aí começou a desenhar outro.
Não, mas eu botei o
É pra ter editado, tem que botar para mim no WhatsApp. No sorteio. É, viu? Vou botar o PS. Embaixo, tá? WhatsApp. Ah, é mesmo? Bora? Vai, pega essa revista e chega no papo. Não, mas eu acho que é o meu vocabulário. Quando tu quiser sair do chá, você sai. Mas eu tomar meu não é isso que eu vou ficar. Eu acho que isso foi uma
Okay, so who wants to come next?
railroad, Pablo said that there are several points in the plane, and we want to find a line with the same amount of points in each side of the line, and also the sum of the distance in each region have to be the same. And well, we have the same for each side. We have the same sum of distance and the same number of points. So the average distance has to be the same. So if it is the center of mass of the points in this part, and this is the center of mass of this point. These two distances have to be the same because it's the distance, the average distance. So the midpoint of this segment have to be on the line, but this point is the center of mass of all points because it's the center of mass of these two center of mass. So the center of mass of all points necessarily is on the line. So we take the center of mass and order in circular way all the points and compute these vectors. And also this condition is with this condition we have the sum of distance of these points are the same sum of distance of these points. So yeah, now we just find a line with the same number of points. That condition is greater than the problem. And so we compute these vectors or sort these vectors. If it's the point I plus 1 I plus k, and we need only that this angle is not 0, and this angle is not 0, and this angle is smaller than p, and also for this angle. So we check for every point this property, and the time is n log n for sort out the points.
There's a lot of question faces. It seems easy because he explained in like 5 minutes, but it's not easy. So I will try to do a quick recap of what he just said, and then I'm going to explain an alternate proof of this fact, actually, a slight generalization of this. So what he's saying is, okay, so suppose we have a solution, right? We have a line that has half the points on this side, half the point on this side, and the sum of the distances of all the points on one side is the same as the sum of the distances of the points on the other side. Okay? So let's compute this. The center of mass is actually the average of the points. Okay? Because there's no way. So what he's saying is that the distance from the center of mass to the line is the average of the distances of all the points. Right? Since the number of points is the same, the distance from the center of mass to the line has to be the same. Because it's proportional to the total distance is just this average times the number of points. If the number of points of both sides is the same, the distance also has to be the same. Okay? Then having this, it is true that the center point of this segment lies here. Because these two triangles are exactly the same. Okay? Because these two angles are the same, and then these two distances are the same, so these two triangles are these two angles. Okay? So, and since this is the center of n over 2 points, and this is the center of n over 2 points, the weight of each center, the relative weight is the same, because it's the center of the same number of points, so this middle point is the center of all the points. So then we can calculate, and then just calculating the average of all the points in the input, we get 1 point in the line we need to build. Okay? Any line that is a possible solution, then it's going to pass through the point. Then, using that point, we can sort circularly by angle all the other points. And then, since we know how many we want on each side, we want that, like he said, we need from pi to pi plus k, which is pi I plus n over 2, are going to be on one side, and then from I plus k plus 1 to n, and from 0 to I minus 1 is going to be on the other side. Okay? And that for some I that we don't know. Okay, but we can try every I to see if this happens. And for that to happen, it has to be that the angle between the I and the I plus k is not too big. So it's not more than 180. Right? If it's not more than 180, then we can put the line that just, if it's not more or equal to 180, or to pi. Right? If it's a little bit less than a plane angle, then we can put the line in a way that doesn't really cover. Right? So we only care about. So because everything in the mid, I mean, if this point and this point are on the same side, everything in between is going to be on the same side because of the angles, right? Of a line that passes through this center point. Okay. So so to check if a given value I is suitable for this partition, we only care about the pi minus 1, the pi plus k or pi plus n over 2, and the pi plus n over 2 plus 1. Okay? Because all the others in this on the downside is going to be in the middle of these two, and all the ones up here are going to be in the middle of these two. Okay? So we check if this angle is less than pi or less than 180, and this is also, then there is some line here that we can pass. If one of these is more than 180, then there's no line that's going to leave them both on the same side together with all the ones in the middle. Okay? Good. So we check this condition with just with a couple of constant time operations. We check both angles for each I, and if for some I we find that this comparison is true, then we have a solution. And if for no I this happens, then we have no solution. Okay. This is great, but this is like really the main property of the problem, right? Once you know that the line goes through a point, then you can do this sorting, and everything becomes a different kind of problem, right? But without this property, I mean, like moving things in 2D space is complicated. So this property, so this is a nice geometric proof, but this property is actually true without requiring that the number of points on each side is the same. So if we have some line such that the distance from all the points on one side to it is the same as the distance from all the points on the other side to it is the same, then the line passes through the average of all the points. And this is because, so I'm going to explain my proof for this because I think the technique is good to do fast proofs, or at least really fast arguments for things, and then this is useful for contests because in a contest you don't really want to be writing a really long proof. This is not very long, this is also a good argument, but I think the technique I have is also nice. So let's start with the easy case. So let's suppose that the line is horizontal. Okay? Then we have some points here, and we have some points here. And then to calculate the distance, really the x-coordinate of the points doesn't matter. Right? Because the distance is just the difference between the y-coordinate. So this is the line y equals to some constant, right? And the distance to a point that is below is chi minus the y-coordinate, and the distance to the point that is above is y minus k, where y is the y-coordinate of the point. Okay? So the x-coordinates do not matter, and really all that matters is which is the value k, and we have a bunch of real numbers, or integer numbers, and the point that makes all the distances the same is the mean. The sum of the distances of both sides the same is the median of the, sorry, it's the average of the points. Okay? This is way easier to prove in one dimension. Okay? So for this one, so then we can just rotate the problem. If the line is not horizontal, we rotate everything. Because if we rotate, I mean, if something happens, then it has to happen after we rotate. So when we rotate the problem, the thing is that not everything is, I mean, you could think, okay, if instead of the average we took any other function of the points that lies on the line, then this is also going to be maintained when we rotate. But that's not true, because we need to use a function of the points. We need a function of the points that gives us a point in the line and that is maintained through rotation. Okay? Because to find the point on this line, we really need the average of the y-coordinates, and we can choose any x-coordinate. Right? But choosing any x-coordinate is not going to be a function that is maintained through rotation. Okay? So once we rotate, doing the same procedure is not going to give us the rotated point. Okay? But the average is maintained through the rotation, because the average is a linear function, and rotation is just matrix multiplication. Right? You have several points. So 1, 2, 3, and we take the average of all these points. This gives us some u. Okay, let's suppose we rotate this, but by some angle. Rotating is just, there's some matrix of cosine and sine of the angle that rotates the points. Right? So the rotated points is m times 1, m times p2, for the same matrix m. Right? So the average of all of these, by linearity, is m times q. Right? Because we contain just m, because the matrix multiplication is associated with it. Okay? So then that means that the average is maintained through rotation. Therefore, if the average of the points lies on the line here, then it lies on the line in any angle the line can have. Because we rotate, we find the average and we rotate again. Okay? So these things that are invariant through rotation are really good for proving things, because it's not only on this case that it is comfortable to work with lines that are horizontal or vertical or something. Okay? Good. Any more questions or comments or? No? Okay, great. So, who comes next?
So my problem was laser beam, and basically you have a grid with many points. And you have to know how many subsets you can build with rectangles. It means
I have two kinds of rectangles, like this. Means the height is infinity, and the width right? And the x is parallel to x and y. So I have two kind of rectangles, like this and like this, right? And I have to know how many subsets I can cover. Different subsets, of course. So suppose that I have just this kind of rectangle. How about you solve this? So you can sort the points by x, right? So you can sort these points, and you can start with this point. So these form a subset, right? Just like this. So you can iterate over these points. This form another subset until you have the width less or equal than w, right? So I have n points. It's less than 1,000. So this is n squared, so I can do it, right? So for just one direction, it's just for this rectangle, I can solve n squared, and it's solved. So now when I do with this rectangle, I do the same thing, but I have to, I can't count the same subset. So to know if some subset is already counted, I can just maintain a set of coordinates. Why? Because a subset of points is identified by, suppose that I have this subset, right? So this subset is identified by this rectangle, right? So for each subset, I have just to keep the x minimum, the minimum x, the maximum x, and for the same for y. So if I have this, when I do for this rectangle, I just have to know if some subset has already been counted. And the solution, the number of subsets, so it needs to be n squared, right? Because for x I have maximum n squares, for I 2, so it's gonna be n squared. But my solution didn't pass in time, so I don't know, maybe it was a problem with time limit, I don't know. And you can do it just n squared if you preprocess with random minimum carry. So when I have to know if a set has already been counted, I just have to do a random minimum carry, so you can reduce, eliminate the log. But I don't know, I don't know, my solution didn't pass the time. Maybe it was a time limit problem, or it was a test case problem.
Okay, let me. I will try to say the same again, but maybe a little bit more formal. So let's consider first the things with infinite height and fixed width. Okay. So since the rectangle has infinite height, then that means that for this the y coordinate does not matter, right? It's only a matter of which. We only need to really process the x coordinates and then check the subset. Okay? So we have a bunch of So we have a bunch of real numbers or integer numbers, and we sort them. We sort them by x coordinate. Okay, and then we want to know which contiguous part, which, let's call it subarray of this, have the difference between the first and the last less than W, or less than or equal to W. Okay? If for a contiguous part of this, the difference between the first and the last is less than or equal to W, then that means we can put the laser width there. If it's not, then that means this is too wide for us. Okay? Then, if we want to count this, we only need to count this number. But the problem is, and then for the horizontal beams, we can do the same, but in the y coordinate. Okay? With exactly the same procedure in the y coordinate. The problem is that there may be some subsets that we find a way to kill them or to put them in the x coordinate, and the same subset we can process in the y coordinate. Okay, so if we just count, we cannot just count in the horizontal way and the vertical way and then add the two amounts. Okay, for instance, any single point, well, single points that have unique x and y coordinates are going to be possible to find both in the horizontal way and the vertical way. Okay, so what he says is that we need to record, let's say, all these subsets. Okay, so what we do is we try every possible subsequence of these. There are n square of those. Okay, and for each of those we check whether the width is small enough or not. We can do a little better. I mean, as soon as we find one that is too wide, we know that if we keep going, if we can keep making it larger, it's not going to work. But I mean, for complexity reasons, we can just test every possible subsequence. There is a contiguous subsequence, and check whether it can be killed or not. When we find one that we can, what we need to do is record the set. And his idea is that, so suppose we have a set that we can kill both horizontally and vertically. Okay? First of all, this means that this is less than W. But this is really doesn't matter. What matters is that if we think of the bounding box of a set of points, we take a bounding box, anything inside the bounding box is going to be contained, has to be contained in the set, right? Because of the way we are considering which sets we are considering. Okay, we cannot have an extra point here that is not in the set, right? Okay. Then we can this x min and x max, y min and y max is just identifying the subsets by their bounding box. And the good thing about the bounding box is that we can calculate it pretty easily. Okay, it's just taking the minimum x coordinate is the x coordinate of the box, the maximum of the x coordinate is the right coordinate of this side, and then this is the maximum x coordinate, y coordinate, and this is the minimum y coordinate. Okay, and then here, but for instance in the horizontal, we know of course we know which is the minimum and maximum x because this is the way we are generating. So what we have to remember is for each x coordinate, which is the minimum and maximum y coordinate that is contained, that have a point with that x coordinate. Okay? So when we sort, we have a unique, so if we have several points with the same x coordinate, so x, y1, x, y2, x, y3, when we sort here, we put the single x, but we remember that we have some min x, some min y equal to y1, and some max y equal to y3. Okay? So when we iterate all the subsequences, we first we do an outer for the left end of the sequence, and then when we start making the sequence wider, we can accumulate which is the minimum y and the maximum y we've seen so far. Okay, so as to save us for making another round to calculate the minimum y and maximum y. Okay, and then when we get to iterate the sequence, we have both the min x and the max x and the min y and the max y, which represent the bounding box, and then we have this small representation of the subset of points. So we insert this representation in a set or something like this, and then the size of the set is the answer. Did I say it correct? Yes. Okay. Okay. Yes, and so the. Okay. So are there any questions, or more comments, or other solutions?
I have another solution, but it kind of uses hashes.
But it's just like putting this in a hash set, or it's really different?
I know, it's really different.
Okay, so
Do you want me to explain?
yeah.
Well, it used the idea that Kuba taught us on the last week about the shore of elements. I don't know if you remember. So for each of the points, I associate a random number up to this one. And then I sort the points for the x, and then for every interval with length less than w, I get the shore of all the elements and put on a set. And then I count the number of different elements in the set.
But when you say short, it's XOR, right?
Yes.
Okay.
That's
You know, because in Spanish it's not pronounced X, it's pronounced. I just want to make sure I understand.
okay. That's basically that. But the set is a bit slow, so I had to sort. Put on a vector and sort. Is it clear?
Okay. Any other comment or solution or question or? Okay. So we have a couple of more problems. Who wants to come and make their problem?
So my problem was called Rabito and Bones. I would like to apologize because someone changed the problems statement and made a couple of mistakes. It was about graph theory and game theory. The statement described a game that was played with two dogs. They were given undirected graph with positive weights on the edges. And there was a special vertex 1. So it's just like usual games with an impartial game with two players. There is always a player who wins and the other player loses. So they play in turns. they have some special bombs placed in some of the vertices. So let's assume that they have this one bomb here and another one here. The statement says that one dog can move this bomb towards this special vertex only if the edge he uses is part of a shortest path to this node. That is the first condition, and the second condition is if there are several such edges, he is going to use one that allows him to use the maximum number of edges to reach vertex number 1. So there are two conditions. One is about shortest paths, and the other condition is if there are several such edges, use the one that maximizes the number of edges until you reach this one. So it's about longest path. So the intuition is that first you have to reduce this graph and then try to apply some game theory to solve the problem. So first we are going to reduce the graph and then solve the game. Is it clear until now? Okay, so this is a somewhat standard problem to check if an edge is part of a shortest path to a given vertex. So we have this edge from U to B, and we want to know if this is a part of a shortest path from U to 1. And this holds if the shortest distance from 1 to U is equal to the shortest distance from 1 to B plus the weight of this edge. So what we can do to check the first condition for all movements is to use Dijkstra's algorithm, and for each edge we check this condition. So we can check the first condition. And now for the second part, we use a simple fact that once we reduce the graph with this observation, what remains is it's a DAG, right? Because when we deal with shortest paths, we can never end up with a cycle. So once we simplify with this condition, we end up with a DAG. So it's not the same example, but just a general one. And now you can see that the second condition translates into, for each vertex, find the longest path to vertex 1, right? And this can be solved again with standard dynamic programming. And we can check again this condition quite easily. So once we have performed these two steps, we can see that if we have a bone here, then one of the dogs can move it 1 or in distance 1 or 2, because that is the longest path to this vertex, right? So we can see that each bone translates into a pile of size equal to the number of edges until vertex 1. So for instance, if I have one bone here, it translates into a pile of size 2. If I have another bone here, the longest path is this, which uses 3 edges, so it translates into a pile of size 3. And I do that for each bone. So now the game is, we have n piles of arbitrary size, and we have an additional parameter, p, and the game consists of picking, of choosing a subset of size at most p, and then removing any number of stones you want. So if p equals 1, that is standard nim, right? You just pick any pile and you remove whatever you want. But in this problem, you can pick, say p equals 3, then you can pick this one, and this one, and you can remove whatever you want. Or you can pick just 2, these 2, and remove whatever you want. or just pick one and do the same. So as it happens with NIM, there is also an elegant theorem for this. Well, actually, this is called Moore's NIM. There is an if and only if condition for this, and it says that a position is losing if and only if when you write the sizes in binary form. The ends are the byte sizes. You write all the sizes in binary form, and then you, just like in NIM, you perform addition of the bits by column. You can prove that a position is losing if and only if in every column you take it modulo p plus 1, and the result, if the result for each column is 0, then the position is losing. Otherwise, it's a winning position. And you can see that for the special case p equals 1, you are basically taking the sum modulo 2, which is NIM, right? And well, it's not very hard to prove this, right? For instance, assume we are in a losing position. Assume we are in a losing position, so that means there is a column for which the number of ones is not a multiple of p plus 1. So I cannot get to a position where in this column, if I take the mole of p plus 1, then all the ones are removed, because in one move, in one turn, I'm allowed to pick at most p. Right, so I will never be able to cover all the ones in one column. So that's the easy way to prove that if you are in a losing position, every move is going to take you to a winning position. And then what remains to prove is that if you are in a winning position, then there is at least one move that takes you to a losing position, and that's the tricky part of this theory. But you can prove it on your own. Is there any question?
Solution or comment or take up one more.
What's called for factors was just these things are better. We don't have a graph, and each node will be a factor. So initially, your factory will have one worker, and each factory will be paying CI points of gold. The tricky part was that after a worker worked here for 1 day, you have to move another factory, or actually get here. But what's fixed? So every factory just had one next factory. Yeah. So I ended up having something like this. had an amount of code that he wanted to reach. So after these steps, we'll have like, for example, the worker one. Now after 3 days, the worker that started in the other one will make like 10 points. Percent will go here, here. And well, if that was the amount of coins that you wanted, the problem will be solved because it already happened. And the question was, what was the minimum time that every worker will make enough to reach the savings? Was what? The intended solution was like the speed up of the word first. You can think with this problem, I guess you can have a vector that will resume a step that will tell you worker in the first factory will win like your 3 coins and will move towards the preparatory zone. So I will go 3 coins and we'll end up with 2. Then it will make a 2 and we'll go 3 and so on. So it will resume my first step. What can I do is I can name this D. And if I copy it again, this here. I will have the answer when I just need 2 steps, which will be here. I will end up in 2, and then I will do another step. So I will end up in 3. And the first one, if I zoom this, I will end up with something like this. I will go to 2, and then I will make up 5. And we'll end up with the factory. No, factory is here. So this will be the solution. 1, 1. So if I apply t times and t is the answer, all of these coins will be more than the number of coins that the worker will need to reach these savings. So that will be the answer. But this is too slow because I will have to do it 3 times and step will make n until it will be up to 7. So this was too slow. But you can see that in order to get, for example, the answer for 4 steps, I could do the same. I could put here P2, then apply the operator, and do again P2, and then you get P4. That will be the answer for the first one in 4 steps, the second one in 4 steps, the third one in 4 steps. And again, if I wanted the 8 steps, I just apply here and here. So this little merge thing have a nice property. If I apply t times, I will name this supergraph function f. I will get 2 things. It will be p1 and p1, and we'll do that again. Then I can apply again f, p1, and then again I will get p3, and then 4, 5. So it seems like a matrix multiplication. So I can apply the same technique. I could do matrix exponentiation and replace the operator of multiplication for this function. So I will end up with, for t, I will end up with n log t operations. So I will just need to fix up this key. And I do that with a binary search on the result. I could say fix a result and say, well, if I can reach my savings at this point, then I will end up reaching that same amount and the time t plus 1. So I can end up the high. Well, it's like a standard binary search, so I will end up with another factor of t. Well, that was
the idea that I applied. But my friend Mr. told me that you can actually take this login and then well, actually not even log T, this login. I didn't thought about it, but was something like this that you can go because it's a graph that just have a degree of 1. It will be just like a loop. All the components will be like this. So you can just find out a node and the cycle. So you move the node towards the cycle, and then just let's say that's the summation of all the wall that you get in the cycle, and you just divide this number. Savings. There's this part, CP, and this will be the number step until I have to just do one more cycle, and you apply regularization on the summations. That was also pretty neat, but the expected solution was like that. Any questions?
So I want to say some things about the first solution, but so first, did anyone understand this solution about the cycles? It requires really careful math because there's several like edge conditions. I would say, but basically, since everyone is going to be making a cycle, the fact that the number of steps can be really big doesn't really matter, right? If the number of steps is really required is really big, then it's just a matter of okay, some number of cycles and then a little bit, right? And the cycles can be removed by doing this kind of math, right? So we basically take however many cycles that are needed, and then reduce to a situation in which t is small. I mean small is like in the order of n. Okay? One actually t, but t divided by the constant. Okay, so this can be done I think in linear. But for this solution, so for this kind of iterative squaring exponentiation or divide and conquer kind of thing to work, we only need like something like associativity of f. Like so, have a notion of the fact that f squared or f cubed is something. We don't really need. I mean, it is true that this matrix multiplication. I will tell that in a minute, but we don't really need it to be exactly matrix multiplication. Anything that we can represent, any function that's such that we can represent the transformation of several steps to just one object is going to be. This idea is going to work. Right? You don't really need it. Because here, if you do this with exactly matrix multiplication, like write down the matrices, it's going to be slow, right? Because here, one operation, which is translated into multiplication, it's only taking linear time in the number of elements, right? If we actually translate to a matrix, it's going to take cubic time, or n to the 2 point something if you implement some algorithm that is better in complexity but is worse in practice. So really, matrix multiplication is just it's a good way to see it, but it's not a good way to implement this. But the good thing about matrix multiplication, so let me tell you why this is matrix multiplication. So we have two things, right? As long as if we want to see it as matrix multiplication, we cannot really multiply a vector of pairs, or we can, but it's annoying to see it like that. So let's split that vector into two. We have the positions, which says for each worker at which node it's standing, and we have money or something. How much money he accumulated over time. Okay. So when we go for the positions, when we want to go from one state to the next, we just need to multiply by the matrix that represents this graph. Right? It's going to have just 1, 1, just a single 1 and not zeros in every row. So it's going to send you to the correct place. Okay? And for the money, we just need to multiply by the matrix that contains the weights in the line. Okay? It's kind of a Fibonacci matrix, but no, a matrix that is used to calculate linear functions, linear recursions. Okay? We need to sum the current value plus some constant that depends on the position. Okay? So we have two matrices. And then we can exponentiate the matrices and do several steps by multiplying the vector by the exponentiating matrix. And then assuming if matrix multiplication and that means only a logarithmic number of matrix multiplication. The good thing is that we can do that much faster in this case because the matrices are really have a lot of zeros, right? Like the positions, we don't really need the matrix multiplication because we have a small number of ones. Similar to a permutation matrix. But if we have something like a generalization of this problem in which we have several edges going out from each node, and then the worker chooses uniformly at random where to move, not optimally but uniformly, random, then we can have, or even with any distribution of probability for the outgoing edges of each node. Here you can think of all probabilities are 1, right? Okay, we can also translate that into a probability matrix, and the expected position is going to be multiplying by this probability matrix, right? So if you're here, you have, I don't know, 0.3 probability of coming here and 0.7 going here. Okay, this is also some matrix multiplication. Okay, and by exponentiating those matrices, we can get to the expected amount of money each worker can make after these steps. Okay. It's important that, so the problem in this, the generalization of the problem in this case is how many steps do we need to fix in advance to ensure that the expected money is, I don't know, some number, right? This will be the translation, which is not the same as what's the expected number of steps that the worker needs to reach this amount, right? This is different because whenever he reaches the amount, he's ready to stop. Right, so you are going to be making the average of different numbers of steps. This case is taking the average of all paths of a fixed number of steps. So it's not the same. Right? This can be the other kind of problem in which when you reach some condition, you stop, and it may take different amounts of time to reach the condition. It's much more difficult in general. But still, this other thing is a generalization of, and it just works out the same. Right? Or if you think about it in this fashion, it's also the same, only you have to, instead of just keeping amount of money and amounts of and positions, you have to keep like expectation of money and position. So I can be in this position with this amount of money, or this position with this amount of money, and for each we have probability. Okay, so worker 1 after n steps is going to be with probability something in this here with expected money this number. With here with this probability and expected money something. Okay? The good thing is that all the paths that lead to a single node can be accumulated into just one state. Right? We add up all the probability and we calculate the expected money. The expected money is just the money we get from the money that each path gets him, multiplied by the probability that that path was chosen. Okay? Given that we ended up there. Okay, so it's going to be a little bit slower because for each worker we cannot just keep one position and one amount. We have to keep one probability and one amount for each node, but still something that we can do in the So the t part we can reduce a lot. I mean, t can be as big as necessary, and really it won't have a big effect on the complexity. It's just logarithms, right? Of course, it's going to be slower in n. Okay? Okay, so let's have another break. So there's only one problem left, and I was told that they didn't want to explain because they thought everyone already knew the answer. It was the simple problem of this set. So let's take a little 10-minute break, and then I will say some more things, and we can go to. Okay? Okay, guys, let me just make a couple of remarks about today and tomorrow and maybe Friday contest, and then we can just or keep discussing here if you want to make more questions or whatever. So the idea is for today afternoon we are going to have a full contest, so it's all problems are taken from some regional. And I think the difficulty is more or less comparable to the Latin American regionals. So, and you know how good you are at solving Latin American regionals. So try to take it as a contest. So be focused and not distract, do not make shows with the other teams. Try to take it as a real contest, not like yesterday or maybe even the first day. Right? If you're going to have easy problems and medium problems and hard problems. And so the idea is that you take it as contest. So I know that in a regular contest, especially with the easier problems, it's possible that you don't read some of the problems. If maybe some teammate read it and said, oh, I can solve it, this is not really too hard, and to solve it, and you didn't even know the problem existed. That's fine, but after the contest, before tomorrow morning, everyone try to read every problem so you already know the statements, and maybe even if you can take some time to think about it and discuss it with the team, the problems that some teammates solve or the problems that nobody solved, try to keep discussing so that tomorrow morning you are better prepared to discuss the problems. If I'm not mistaken, the winner of the regional got like 9. When the actual regional took place at the end of 2013. And then tomorrow afternoon, what we're going to do is tougher test with just difficult problems. Like something similar to the first day, maybe not that difficult, but all difficult problems are easy problems. So the idea is like tomorrow you can also take it as a test, but how to face a really tough test. Like not jump into finding the trivial problem like you may do or try to do in the regional, in our regional or maybe even tomorrow, but like slowly read everything, try to identify among difficult problem which is less difficult for you, and that type of thing. And again, also for tomorrow, also after the contest, always try to read the problems and keep discussing so that when we discuss it on the board the next day, you have more idea in your head and you can absorb more of what is said. Okay, so also there's a synchro match from top color tonight. It's kind of late, and I don't know how much do you sleep, because when I was your age I didn't sleep much. But so if if you participate tonight, then if someone is going to participate, let me know or send an email to the list or to me, so I read the problems, and maybe if you have some questions, we can discuss them tomorrow at some break during lunch or something. Okay? Okay, so let's go to lunch. By easy, I think it has a short code, but it's pretty, I don't really remember it right now. The code was developed for the programming solution, and then I wrote some mathematics friend after the original, and I told him the problem, and he thought about it, and I said, oh, well, if you do this and this and this, and I think I just read the problem, and it is not working. Okay, so the code is. So the idea is the following. So the observation, the key observation. So if anyone else wants to hear, I'm going to explain the code, not the problem. So if anyone doesn't know this is very so the idea is you have the thing here, and you know how much you have to move up or down whichever the wheels. Okay. And then the moves are choosing some contiguous subsequence and moving it up or down. Okay. And of course the order of this is important. So basically we can represent the contiguous moves as some set of intervals. Some intervals and for each interval, I will move up. And then there are some pretty things we can say about this set. We can put some extra conditions on the set that don't change the optimal answer. If you have an interval that moves up, you cannot have the side and obtain a solution which is equally optimal. So let's assume that this and let's forbid this because this doesn't change the optimal number. Also we can see that we cannot well, of course the opposite. We have a larger down and a smaller labs. We can also forbid that because of the same reason. And if we have overlapping like this, then we can also translate this into so we can also forbid this from happening, right? And if you are overlapping this on the other side, the same happens. So basically, what we proved with these two is that we can assume that each wheel is either moved up or down, but not both. Okay? So, then we can do some dynamic programming. So let's consider the first wheel, right? Because we said that the order of the moves doesn't matter. So let's think of how many moves touch the first wheel, right? So we can do either 20, some number of moves up, or some number of moves down, right? In the case of the first wheel, there's no point on doing. I mean, if this requires that, both this is right? So we can do one move up or 25 moves down. Okay. Well, we could also do something like 51 moves down, 27 moves up. But in the case of the first wheel, there's really no point on doing more, right? Because it may be the case that some wheel has to move more than 26 times. There are examples, but for the first, really, there's no point. If there are 26 moves on the same direction, then we can just remove these wheels. This is the first. We can remove this wheel from all 26 of them and obtain an equivalent solution. I mean, a solution with the same number of total moves. Okay? So let's assume, so either we move into one